computer. Okay, welcome back, everybody. I hope you stay warm this week. We have one quiz on Wednesday and then spring break. Yay! So don't forget everything. But anyway, so what we'll do is we'll be getting through most of chapter 6 this week. And then all we have is 7 in the review after spring break. And then we have our second exam. So that's what we're going to be on schedule for the rest of the semester, assuming we don't have another ice storm. Yes.
So is chapter 6 homework also due Wednesday?
Chapter 6 homework, I think I'm going to put it off till after spring break. I'm making the video for chapter 5 now, and so that should post sometime this week. Okay, and I think I'll just, I think I'm going to push that just so you don't have to worry about it over spring break. Okay, so the homework should be, homework 5 should already be in. Homework 6 is going to be pushed a little bit because of spring break. But other than that, we're good. Okay, so we were talking about R and S. So what's the most important things to remember? Know how to do R and S. Know the prioritization. Know that the only way we can tell these things apart is by their rotation of light. And if one enantiomer rotates it 100 degrees to the left, the other enantiomer is going to rotate it exactly the same amount to the right, 100 degrees to the right. So they're always equal and opposite. Unless you mix them together, then they cancel each other out. So if it's a one-to-one mixture, they'll cancel each other out. But if they're not a one-to-one mixture, we can see it has optical activity. And we can say it has a certain percentage of the optical activity it should have. That's enantiomeric excess. That means you have at least, that means you have 60% of the value given. So that means that the other 40% of the solution is a racemic mixture. So that racemic mixture is half R and half S. So that's how you can tell how much you have from those. And that's an enantiomeric excess. So you got to think of an enantiomeric excess as I only got 60% of the value I was hoping to get. That means that 40% of the solution is racemic. So look at it that way. Okay. So then we said they're kind of hard to get apart. But now I want to introduce you as we go into the next chapter. We're going to learn about stereospecific and stereoselective reactions. So the first thing I'm going to talk about here is a stereoselective reaction leads to the preferential formation of one stereoisomer over the others. Okay, and that could possibly be formed. In this case here, what we're doing is we're taking a hydroxide and we're substituting a chlorine for the hydroxide. So this is a substitution reaction. And when we do that, the substitution happens all at one time. So that means we had to form the new bond on the other side of the chlorine, and therefore we get inversion of stereocenter. So we started with one stereo and we ended with a different one. And that is our stereoselective reaction. It only gives one. Now, there's also stereospecific. Stereospecific means if you start with one isomer, you're going to get another type. You're going to get certain isomers from one starting isomer than you would get from the second starting isomer. So the example I like to use for this one is this. We're going to do, instead of doing a substitution reaction, we're going to do an addition reaction. We're going to add bromine across this double bond. And as it turns out, the mechanism means we're going to add one to the top of this and one to the bottom of this. So when I draw it out as the structure with the bromine on it here, I'm going to draw one on the top and then one on the bottom. And if we're looking at it that way, then we have the methyl group, you know, because this is, we're going to look at it from the top, is going to stick out this way. And the hydrogen on the other side is going to stick out toward us. That means that the hydrogen on this side goes back and the methyl group on this side goes back. Okay, so that's giving us one isomer. Okay, and if it attacked the other way, it would just do that. Now, what's the problem with this material is if I rotate this bromine 180 degrees up, the methyl groups, oh, this is a dashed line, not a solid line. dash, dash, dash. If I rotate that bond so the bromines are in line with each other, the methyl groups are in line with each other, and the hydrogens are in line with each other. What kind of compound do we have now? We have a mirror plane right in the middle now. Now we have a meso compound. So this particular stereoisomer creates a non-optically active material, a non-chiral material. Okay, so what do we do if we do it the other way? Well, let's do the same thing. We're going to put one bromine on top, and we're going to put the methyl group out here, CH3, and the hydrogen back. And we're going to put the other bromine down here, and we have a methyl group sticking out and a hydrogen going back, CH3. So this is one isomer it can create. And actually, it turns out because of that, we can actually draw the other isomer. So we actually have a set of enantiomers in this particular sample right here. And if we go through and do our due diligence for seeing if these are mirror images of each other. And as it turns out, if we rotate around so that bromine is lining up again, we end up with the methyl group mirroring the hydrogen and the hydrogen mirroring the methyl group. So they're not. And these are not superimposable either. So we actually have a pair of enantiomers, R and S, for the cis-butene, but we didn't get that for the trans-butene. So that's what we mean by stereo-specific reactions. Stereo-selective, we only get one. Stereo-specific, it gives us stereo products, but only in one way. Okay, so another thing to remember about our asymmetric centers is that if you're not actually doing the reaction on the stereo center, that stereo center is not changing any bonds. It might not change the R and S designation. But that center is not the thing we're worried about here. Did it change the prioritization of the groups? You're not actually doing the stereo center here. But in this case here, when we substitute the chlorine over here for hydroxide, we don't change the prioritization. We don't change the chiral center, but we also don't change the prioritization. And we end up with the same stereochemistry on both products. If we were to do reactions on that chiral center, then that's where we know we'll have to have probably something changing. Now, in this case here, the ethylene group was a higher priority because we had the carbon, carbon, hydrogen were the three things that this carbon's bonded to. And it only has 2 carbons total in its chain, but it's highest priority at this time. If we did that reaction we learned here in the last chapter, we saw that we could do hydrogenation and that would take away the double bond. When that happens, it changes the priority. None of the bonds changed, right? We just changed priority because we changed the functional group that was on this chain, this thing that was hooked to it. And it actually does change the stereo center. So when in doubt, just reassign your prioritization and reassign your R and S. Okay. So in addition to that, there's the absolute configuration. And the absolute configuration is when we know exactly where each thing is in space. We have to do a special kind of thing like an X-ray crystallography or something like that to tell us we have exactly the R isomer. If all we know is we have one of the two and we don't know exactly which one we have yet, we call that the relative configuration. So we know it's chiral and it's got to be one of these two, and it could have been scrambled and maybe it's racemic, but we know that it's relative to, it's going to be attached at this point and it's going to be one of these two systems. So they might be the same, they might be different, but it's relative to each other. Okay. All right, and the last thing I want to show you is one of the things I said is you want to try to look for chiral things which have sp3 hybridization. Then you have 4 bonds to it, and that gets you into some funny chiral molecules. So as it turns out, silicon and germanium are right below carbon, so they bond 4 times. And so both silicon and germanium create chiral compounds. And we also have the nitrogen is also sp3 hybridized. And when we get that 4th bond and that positive charge, those can be chiral because we have a tetrahedral structure with a 4 bonds and sp3 hybridized. We can also do it with sulfur. And it turns out the lone pair in the sulfur in this case, notice there's 4 bonds, but one of them's a pi bond. But the reason that works is sulfur can go up to 10 valence electrons. And in this case, it's using those 2 extra electrons to create a lone pair to give us our tetrahedral center, and it's chiral as well. Then the craziest thing we have is the last one. It's an example of how you can have a chiral molecule but not have any chiral carbons. Okay, turns out this molecule here, gosh, it's an alene, and is chiral because this right here is out of plane with this right here. So they're twisted like this. And so the entire molecule actually can have a mirror image, a non-superimposable mirror image of itself, but it has no chiral carbons. So the whole thing, the entire molecule itself, meets the requirements of enantiomers, which are non-superimposable mirror images. That's the #1 requirement. That is the requirement for enantiomer. So we just sub-select down to usually 4 bonds, 4 different things, and to make it easier to identify. Questions on that? Yes.
So if sulfur can do that, can phosphorus, since it can also expand?
Yes. Yeah. There's not as many chiral compounds in the literature with phosphorus, but they do exist. All right. So that's the end of chapter 5. Okay. So chirality. So the big things are being able to identify R and S, know your different projections. Your projections include Fisher and Newman, and 3-dimensional wedges and sticks. Those are the 3 projections we used a lot in this chapter. Okay. Now, the other thing we have is our definitions of enantiomers and diastereomers, and know what those are. Know how many stereocenters you can have, how many isomers you have to have if you have a certain number of stereocenters. Let's see, the last thing was practice your activity, the R&S activity, if you haven't already done it. It's going to really help. All right, so take a breath. I am so excited to be in this chapter. We're starting real chemistry, okay? We've done a lot of nomenclature, we've done a lot of stuff like that, and we've done a lot of, kind of thinking about things from just a define everything stage. Now I want to talk to you about how we organize what's happening in a reaction in our heads as we go through these, okay? So the first thing I want to talk about is doing our in-class role taking. Again, at home, you don't have to do this. You're logged on to the website, so that's fine. Everybody got it? Okay. So I get really jazzed about energy diagrams because it tells you a lot about what's happening. I think if you know kind of what should be happening in a reaction, you don't have to memorize anything. You just need to look for the signs of what's going to happen, okay? And so we're going to break it down. We're going to first start with our energy diagrams. And it's just a diagram that has energy on the y-axis and different stages in the reaction on the x-axis, okay? And so we're going to equate those different stages to different types of energy. And we're going to specifically look at the delta G, which is the Gibbs free energy. Now we can relate that directly to delta H, if you remember. So sometimes I'll say, oh, the enthalpy of the reaction is an exothermic or endothermic reaction. So, but those are, again, analogous because we're not doing high temperature reactions. Now, in this diagram, we're going to have a curve, and the highest point in this curve is what we call the transition state. The transition state is where you're going from starting materials to something else. And in this case, we're usually breaking old bonds and making new bonds at the exact same time. Okay, or we're forming new bonds. That's what happens at the transition state. So usually the highest point in energy, and the energy it takes to go from your starting material energy to the transition there is what we call our activation energy. Your reactants will not react unless they have enough energy and to activate them. So, you know, go power twins activate. Oh, you guys are way too young. So, no, okay. So anyway, so that's the activation energy. Okay, so this is what I love about energy diagrams right here. We start with our starting materials. And in this case, we have an Nu ... negative. That's a nucleophile, okay, right? It's a Lewis base. It has a pair of electrons it's trying to make a new bond with. And we have another thing right here we call the substrate. It's just any carbon group with a polar bond. And then the thing it's polar bonded to is what we call the leaving group. And I'll define this again on another slide. So we have our nucleophile reacting with a substrate here. And so it has a certain amount of energy in that molecule. Okay, now we're going to add energy to the system to activate our transition state. In our transition state here, notice that this side is partially negative and this side's partially negative, and there are two partial bonds. The nucleophile is starting to take its electrons and make a new sigma bond. While it's doing that, the leaving group is taking the two electrons between the carbon and the leaving group away with it. So we're making and breaking at exactly the same time. Okay, we usually have those transition state here in brackets, and we have a little symbol we put up here called the double dagger. That tells us we have a transition state. Transition states are fleeting. They only happen instantaneously and they're gone. Okay, now what happens here? Oh, we look at the energy going down here on our thing, and this is the energy of our products. Let's see. There is going to be a chapter, there is going to be a quiz number 6 on Wednesday. Yes. So now the products here have less energy in them than the starting materials did. Okay, that's this delta G. What that means is that we've given off energy in our system. We've given off free energy and we've given it off as heat. So a lot of times it'll say delta H because you will have an exothermic reaction. So with just this little diagram, we're seeing a lot of things. Number one, we're seeing the activation energy. We're seeing how many steps are in the reaction. We're seeing whether the reaction gives off heat or not. We're seeing if we can actually, we'll be able to tell if the reaction's fast or slow on the next, in a couple slides from now. So this gives us a lot of information. And if our delta G is greater than 0, we've given off energy. We've given off heat. It's exogonic or exothermic, if we're talking about enthalpy. And if we've absorbed energy to our products are higher in energy than our starting materials were, we had to put energy in there and we're storing it in there. And that's when we have an endothermic reaction where it absorbed heat and turned it into bonds, or endogonic, where we've turned it into free energy into stored energy. Okay. All right. So let's see. So let's look at a different curve here. We have a nucleophile reacting with a substrate. We have a big delta G double dagger or activation energy. We still have that same transition state right here, but our new products are higher in energy. So what does that make this reaction? Endothermic or exothermic? It's endothermic. It has more energy in it than it started with. It had to absorb heat to store that energy. So here we have an endergonic or endothermic reaction. And that's how you tell. You just look at the relative position of the starting materials and the reactants. Now also this right here is big compared to the one over here. We need to take a look at that, okay? The big delta G or the big activation energy versus a small activation energy, it means something. Okay, so let's talk about that delta. Let's talk about that activation energy. The greater amount of energy it's needed to break bonds, the slower the reaction. That means the higher that peak is, the slower the reaction will be. Okay, so that's important to know. It doesn't mean it's not going to happen, but it means you have very few molecules that have enough energy in the right place at the right time to do it. And that's why it's slow. You have to wait for it to, all the stars to line up for them to react. Okay. Now, the structure of the transition state is at highest energy because you're making and breaking a bond. You're shoving stuff together that really wants to repulse it, right? So when we have this transition state, it's at highest energy because of this bond making and bond breaking. We can't have 10 electrons around our carbon. So those 2 electrons coming in have to be pushing out 2 electrons as it goes. Okay, and we demonstrate that with these partially drawn lines here. And notice the charge. The nucleophile now has a partial negative charge, and the leaving group now has a partial negative charge. The nucleophile had the full negative charge when we started. So that means the leaving group C is taking its electrons with it as it leaves. And if we look at the final products here, oh, we're doing it the other way, sorry. C is the nucleophile. And the A is taking the electrons away when it leaves. Okay, so that's for a one-step reaction. We said we had certain reactions that happen all in one step, and those were called concerted reactions. Okay, concerted reactions, one-step reaction. Cool thing is, when we looked at our energy diagram, we had one peak, one transition energy, one transition state. So we have a lot of benefits to this. It happens all at once. We only have one activation energy. We have one transition state. But not all reactions happen that way. So let's look at what a reaction would have if it had 2 steps. Okay. So in the case of this, we have our first transition state is actually breaking a bond with the hydrogen. So what's happening here is our electrons from our double bond, the electrons in our double bond make it a nucleophile. The electrons from the double bond are looking for a electrophile, right? The nucleophile is looking for an electrophile. In this case here, this partially positive side of the HBr is our electrophile. So these double bond electrons are going to reach out and start forming a bond with the hydrogen. So that's why our dotted double lines are here. And the bromine is leaving with its 2 electrons. That's why this is partially negative charge. So our transition state, our first transition state, is the forming of a bond with hydrogen, the breaking of a bond with hydrogen. And that's going to give us this as a compound. It's an isolatable compound. We can see it, we can analyze it, we can look for it. This bromine is an isolatable ion. We can see it. So that makes this an intermediate. Okay. A transition state is just this instantaneous making and breaking of bonds. But an intermediate is something that you can actually see, analyze for, and then probably reacts again. Okay, so in this case here, now we have the bromine, which was kicked out by a nucleophile, is now a nucleophile. And the carbon, which was the electrophile, because it had the double bond, now has a positive charge. Positive charge means electron deficient. It's a Lewis acid. And so we're going to react our Lewis acid with our Lewis base, having the electrons from here come in, create a new bond. And this is our second transition state. Creating a new bond is our second transition state. And then once it's done, we have our final product. Do we understand the difference between transition state and intermediate? Okay. Transition state is making and breaking. The intermediates are individual compounds. Okay. So what would the reaction diagram look like for this? Well, we have two transition states, so we have to have two activation energies. Okay, so let's take a look at that. So we're going to start with our alkene here. Those lone pairs, I mean, the pi bond is going to act as those two electrons reaching out to make that first bond. And if we look at this right here, we have this big delta G right here in our first step. And this is our transition state here because bonds are being made and broken at the same time. And then that gives us this. Wow, look at how high energy these intermediates are. That has so much more energy than this did here. So it absorbed, it used the energy here to create that high energy state. But the cool thing is we now have a nucleophile and electrophile, and they're going to react that way to form our different second transition state. Now notice how small that second transition state is. So that means this second reaction happens very, very, very quickly. And so really what we're probably waiting for is this first step to happen. And then as soon as we form those intermediates, look how high in energy they are. They want to react. They're really high in energy. It's like they want to react with something, and so they do. And when they do, they cascade down into our products. Okay, so this is a two-step reaction. It has two different transition states, but one transition state is harder to get to than the other. And so one's going to be faster than the other. Okay. Do we see how our two transition states have each their own activation energy, and how when we have two transition states, we usually have an intermediate? Okay. Okay. All right. So let's do a little bit about kinetics and thermodynamics. So thermodynamics doesn't care the path you took. It's what energy at the beginning and what energy at the end. So we just have to look at the beginning and the end of the reaction and say, oh, it's thermodynamically favored because it's exothermic. We can see that from just looking at the two ends. However, kinetics is all about the time it takes things to happen, right? So in the case of kinetics, we can also interpret whether reactions are going to go faster or slower by the height of the activation energy. The higher the activation energy, the slower the reaction. Because you have fewer and fewer molecules with enough energy to do it. Okay. Now, how can we speed up a reaction? If it's a kinetic reaction and it's related to the activation energy, that means we can do two things. We can increase the temperature so more molecules have enough energy, or we can increase the concentration. We have more molecules. More molecules means more times they hit, the more times they hit, the more they're going to react. So we can change the kinetics of the reaction by increasing the concentration or increasing the temperature. Okay. So the kinetics here, the delta G and the delta H and the equilibrium are not affected by the reaction rate. The enthalpy of the reaction is not. It's going to be exothermic. It'll be exothermic fast or slow, but it's still going to be the same amount of energy given out. So it doesn't matter. Okay, so how do we kind of tell the difference between different types of reactions based on whether it's concentration or whether it's one step or two step? Well, we have a way to do that when we talk about our rate laws. So a rate law is going to tell us a lot about the reaction. Number one, it's going to tell us whether or not the reaction is concentration dependent for all ingredients or just one. But it's also going to see, how fast the reaction will go anyway. So in the case of that, we have a rate constant. The rate constant is independent of concentration. Okay. So the rate the reaction goes, that constant is independent of concentration. So that means if I said on the last slide that by changing concentration, we can increase the rate of reaction or decrease the rate of reaction. So we have to take the constant that has nothing to do with concentration and multiply it by the concentration of the reactants. And when we do that, we end up with what we get is our rate law. Okay, so our K is constant, our concentration of reactants is here, and that equals the rate of the reaction, which means we can take a known reaction and change the concentration and predict what the rate would be, because we already know what it should have been. So let's take a little deeper dive into the equations here. Okay, so the rate constant and the energy of activation are inversely proportional. Okay, a high rate constant means it's going to go fast, which means you're going to have a low activation energy. Okay, and if you had a high activation energy, that reaction is going to go very slow, and so you're going to have a low rate constant. Okay, so they're inversely proportional. In single step reactions, both of the ingredients that meet in that transition state, their concentrations are important, because if you have to both components there at the same time at the same place. So by changing the concentration of either one, it's going to change the rate of the reaction. Okay, so in this case right here, we're going to have one kind of rate law. And in the case of multi-step reactions, we're going to have a different kind of rate law, because the way the reactions are going differently. So we want to think about that. Okay, so in a multi-step reaction, the slow step is what we call the rate determining step. Okay, now, why is the slow step the rate determining step? Well, let's look at this energy diagram again. We saw we had this huge activation energy to get to that intermediate, but we saw that intermediate was very reactive and a very small activation energy. So which one is the faster reaction? The one with the big activation energy or the one with a little activation energy? The little one, right? So that means the first step is the slow step, because it has the high activation energy. So we can see that that's the slow step. And so that's our rate limiting step. It can go no faster than that first step. Okay. So that's our rate determining step. So let's look at the way we would do our rate equation for something that has two steps. Well, or for something that has the one step. In a one-step reaction, we want to have both of these things at the same place at the same time. So what we're going to do is we're going to say, okay, we're going to have the concentration of the substrate and the concentration of the nucleophile. They're both important because they have to be there at the same time. So that means there's a 1 on the exponent on this concentration and a 1 on the exponent of this concentration. And if we add those together, we get 2. So this is a second order rate law. It's dependent upon the concentration of two different components. Second order rate law. Okay, so most single step reactions are second order rate law. Sometimes they can be third order if you have a third reactant. That'd be a very weird reaction, but I'm sure there's one does exist. Yeah. So, but in a multi-step, it's a little bit simpler. Okay, in a multi-step, we only have to take into account the slowest step. And that's because if you have one little restriction in your flow of your reaction, and the other steps are much faster, then they're just going to continue on to product. And so only our slow step where we generate our first intermediate is going to matter. Everything else is gone. Little teeny activation energies, very easy. So that means we only have to worry about our first slow step. But what does that mean about our rate law? Well, if that means the first thing that has to happen is we need to break a bond to get to this intermediate, we only care about the concentration of the thing that's breaking the bond. So that means our rate law only has one thing in concentration in it, only has one exponent here, and that becomes a first order reaction. Okay, so what it means is you can react, you can have a whole bunch of this in here, and it's not going to change the rate of the reaction because it can't react until you've made your intermediate first. So it all depends on making that intermediate first. And it's usually the substrate or the thing that we're going to be, the carbon thing with the leading group on it. Okay, so two-step reactions tend to be first order. One-step reactions tend to be second order. Sounds weird, but that's real. Write it down. Okay, so how do we determine reaction rates? Well, we actually measure them, okay? So in this reaction, we're going to assume it's a second order, and we're going to see how it affects our rate, the rate, not the rate constant, rate constant is constant, the rate as we change concentration of a couple components. So in the first example here, we're going to use about 100:1 hydroxide to this chloromethane, and we're going to measure the time it takes to consume a bunch of the product here. And what we see is we get about 5 times 10 to the minus 7 moles per liter second. So every second you're getting that many molecules to react. Okay. So in the second experiment, we've doubled the concentration of the, we've doubled the concentration of the substrate, the carbon that we're substituting. And the reaction rate doubles. This is the same, this is the same, but that other one was doubled. And we saw it double in there. So let's see if the OH is important too. Let's change the way we did it. So we're going to keep this one back down to the constant number, and we're only going to change this one. We're going to double it. What do we see happen? The reaction rate doubles again. Okay, well, what if we went crazy and just doubled both of them and saw what happened? 4 times. Twice for doubling for the hydroxide and 2 more for doubling for the methyl chloride. 4 times. So in a second order reaction, you double any component individually, you double the rate. If you double both components, you quadruple the rate. Okay. So that proves that this is a second order reaction because we could change both of our components and it changed the rate. So we know it's a second order reaction. Okay. So that's pretty cool. But what if we have equilibriums? We had all those acid-base equilibriums. Well, we can still do that. We just have to think of it in a different way. The way we have to think about that is that the forward reaction has one rate constant. It's the rate constant for that forward reaction. And the backwards reactant has a separate rate constant. It's different. Okay. If the top rate constant is much, much higher than the bottom rate constant, then the reaction is going to lie to the B product. If the back reaction is faster than the top reaction, it's going to lie to the A product. And so what we can do is we can kind of take it, so our equilibrium constant is actually equal to these 2 constants here. And the concentration of products over the concentration of reactants, just like in our equilibrium for acids and bases. So what I want you to take apart from this is that, yes, the rate constant is measured. We have 2 different kinds of reactions, first order and second order, and you can identify it by looking at your energy diagram. Okay, so what order reaction is this?
First order.
First order, we make an intermediate, but it only matters. Notice that we don't even have oh, no, this is a second order reaction, sorry. This is a second order reaction because we have two things right here. We have there. So we have two things. So this is a second order reaction because we cared about those two things. And the second reaction has a very small activation energy and therefore is very fast. So what's the rate determining step? The first step, the second order step. And in the second reaction, look at the transition state. We have two things coming together to form a bond. Is that first order or second order? Second order because there's two things coming together in transition state. So those are second order. And if we look at our one-step reaction, right here, what is this? It's also second order because you had to have both things there at the same time. So the concentration of both are important. Okay. So I don't have an example of a first order reaction, but questions on rate laws, first order, second order, third order? Okay. So now I'm going to switch it up a little bit. We're going to talk chemistry. Okay. So I'm going to remind you that when we're looking for places to react, we're looking for polar bonds. Okay. We're looking for polar bonds because what we're going to see is on this polar bond, this is the partially positive side, this is the partially negative side, and this bond is polar. So if we have a nucleophile coming in, which side is the nucleophile going to attack, the carbon or the fluorine? The nucleophile has a negative charge, it's going to attack the partially positive charge, right? So always look for the partially positive side of your bond. Okay, now, if we look at these as well, if we look at all these, as these atoms get bigger, these bond lengths get longer. And as the bond lengths get longer, the bond strength goes down, meaning that they're easier to remove from the molecule. They're easier to leave. Okay, so the polar bond is where you're looking to find your nucleophile and electrophile attack points, and your length of bond or the size of the atom tells you how easy it's going to be to remove it. Okay, so now let's talk about all the different nomenclature you need to know for substitution reactions. So we're going to do all of the substitution reactions we're going to do with nucleophiles first. And so we're going to call these nucleophilic substitution reactions. Okay, so nucleophile substitution reaction. Got it. So we all know what a nucleophile is because we said that a nucleophile is a Bronsted-Lowry base or a Lewis base. It has a negative charge or a lone pair. That lone pair is going to be used to make a sigma bond. Okay. Now the substrate is the carbon-containing thing that has a leaving group on it. So a leaving group is something that gets substituted off of the molecule by the nucleophile. So it's the one that's going to leave with its 2 electrons. Okay. So notice this little blue line here, right here, they're going to leave with the leaving group. The electrons from the nucleophile are going to create the new carbon nucleophile bond. So we're going from a sigma bond to a sigma bond. And we're using the terms nucleophile, substrate, and leaving group. Okay. So one thing we need to consider when we're talking about these substitution reactions is, number one, is the leaving group a good leaving group? If it doesn't want to leave, that's going to make the reaction go slow. If it doesn't want to leave, the reaction might not go at all. So we need to care about the leaving group. We also need to care about the nucleophile type and strength. Okay. So does it have a full negative charge? Does it only have a lone pair? Those are things that are going to affect its strength. Okay. Solvent effects. As it turns out, as you change solvents, you can change whether a compound can be highly nucleophilic or poorly nucleophilic. And we'll see that. And then substrate. Substrate has to do with the actual the sterics around where the leaving group is. If there's too many things around where you're trying to make a bond, then it's going to go slower than if you only have one thing hanging off next to it. So we're going to talk about the substrate. So in this case here, we're going to take a neutral nucleophile, our amine, and attack the partially positive side of this polar bond. And we're going to have these electrons kick out. And so we're going to end up with iodine minus. And because we have 4 bonds to nitrogen, we've changed its formal charge from 0 to +1. And guess what? It's counterbalanced by the ion. So we've substituted the iodine with nitrogen and created a new compound. And in this case, a salt. So we can do that again with another good nucleophile, right? It's got a negative charge on it. So we're going to take hydroxide and we're going to do that same substitution. It's going to come in here, make a new bond with the carbon and kick out iodine. Notice in the case of here, we have a nucleophile with a negative charge and it kicks out a leaving group with a negative charge. Look for that. That's going to happen most of the time. If we attack with a neutral, we're usually going to generate a positive charge in at least an intermediate. So for example, why I say least an intermediate, if this was a hydrogen, we could get rid of that hydrogen and it can go back down to neutral if we had a base. But look for, if it's a neutral nucleophile, a charged product or intermediate. If it's an anion, you're going to kick out an anion in your leaving group. Okay. So in this case here, we're going to use the methoxide, the conjugate base of methanol. And we're going to come in here and kick in here and give us our new ether and bromide ion. And over here, we have big old fluffy iodine. It's going to come in as a nucleophile and kick out chlorine to give it there. That's a special reaction. That doesn't usually happen, but because of solvent effects, we can make it happen. Okay. All right. Questions? We get all the terminology here. I like the word substrate because it means any alkyl group with a leaving group on it. So we can use any kind of system for that. Okay. Sorry. Muted again. All right. So let's look at some good examples of nucleophiles. Obviously, things with a negative charge are good nucleophiles, right? Hydroxide, thiolate, amide. Look at the carbon nucleophile there, the acetylene anion. The alkoxide, which is the conjugate base of ethanol or alcohols. The conjugate base of carboxylic acids and stuff like that. And so they're usually counterbalanced with some kind of metal, sodium, potassium, or something like that, so that they can be in solution. And then when the reaction progresses, what we end up with is our nucleophile is going to come in, displace our leaving group, and then we're going to end up with a balanced charge at the other end. Notice our substrate was neutral at the beginning. We had a negative and a positive charged species in our nucleophile, and we have a negative and charged species in our product. Now, that's great because we always kick out a negative leaving group. Well, when we have neutral nucleophiles, and we think about the lone pairs on alcohols, water, ethers, and the nitrogens here, what we get from that is that those lone pairs are going to come in and change the formal charge on nitrogen or oxygen. And we're going to have at least an intermediate that's going to have a positive charge. Now, if you can get rid of that positive charge by losing a proton, you can go back down to the neutral species. But you're always going to generate a charged species. And in this case, we're using a base to transfer one of the protons to get to our neutral product and the conjugate acid of ammonia. Okay. So whenever you have a neutral nucleophile, look for a charged intermediate. Okay. All right, so let's look at some common nucleophiles. We have the oxygen ones, hydroxide, alkoxide, carboxylic acid salt as the charged species, but then we also have water and alcohol. Lone pairs, lone pairs. And then nitrogen, we really only have the one charged species. This is azide. But we have a couple neutral ones. We can use ammonia or any of the amines, primary, secondary, or tertiary amines, and they'll generate. Then we do have carbon nucleophiles, the cyano group right here, or the acetylene, but we can also have the vinylene and the alkyl anions, right? If we have really strong bases, we can make those into anions too. So carbon can be an anion. Carbon can be a nucleophile. Then we have the halogens, those are classical. And then we have sulfur. It's big and bulky, but it's stronger in its negative state, but it still has lone pairs, just like oxygen. So it can do it as a neutral nucleophile as well. Okay, so those should be like things you're looking for in a reaction is, oh, that's my nucleophile. That means the other thing's my substrate. Then I just need to get a little more information to figure out what's going to happen. Okay, so let's talk about the leaving group. The nature of the leaving group is actually kind of interesting because you want it to be a good enough bond to be a compound, but you want to be a weak enough bond so it leaves. So there's a kind of a balance there. So how do we know if our nucleophile is strong enough to displace our leaving group? Well, we really need to look for is the better leaving group is going to be the weaker base. That's analogous to what we saw in the acids and bases, right? We were talking about if it was a strong acid, it's a weak base. And when we were doing our acid equilibrium, it always went to the weaker acid. Here, we're going to look at it from the basicity side and say, we're looking for the weaker base. So we'll have to think about, oh, what's the conjugate acid? Where are they on the pKa scale? And see which one's going to be better. So we're always looking for that more stable charge on that leaving group, which means the weaker base is going to be our better leaving group. Okay, so let's talk about some trends here. Okay, as you go across the periodic table here, right here, with those second row elements, you get better leaving groups as you get closer to fluorine. So fluorine's a better leaving group. HF is a better leaving group than water or than ammonia would be. And carbon anion is a very bad leaving group. So you hardly ever have carbon anion as a leaving group. Okay. So, but then the next thing we see is that as we go down a column, we actually see that the acidity increases because of polarization in size, right? So that means iodine is the weakest conjugate base because HF is the weakest acid. So the iodine would be the weakest conjugate base. So that means iodine is going to be the better leaving group for that system. But let's add a couple other things to that. I'm going to show you the pKa's of the conjugate acids and prove to you that what good leaving groups are iodine, bromine, chlorine, and the protonated alcohol. When we have a protonated alcohol like that, the leaving group is actually neutral water. So its leaving is H2O. That positive charge on oxygen goes away because it gets its lone pair back. But look at the pKa. HI has a pKa of 10. HF has a pKa of 3.2. Okay. So if that were true, that means that the conjugate base of this is weaker than the conjugate base of this, making iodine a better leaving group than protonated water. Okay. So now let's look at the ones that are poor leaving groups. You see ever increasing conjugate acid pKa's. Okay. So the break point right here is probably right here. This is where water and alcohol would be. And you're losing hydroxide ion. So hydroxide ion is actually a very strong nucleophile. It's a very strong conjugate base because it's a very weak acid. So now these are starting to get very strong bases. These are very weak bases, meaning the weaker base is the better leaving. Okay. Okay, so nucleophile and basicity are actually different things, but they usually go hand in hand, okay? Basicity is a measurement of how willing it is to get rid of a proton, and it's an equilibrium, which means it's thermodynamic, okay? Basicity is thermodynamic. And, it'll go back and forth and find that even place to where, all the energy kind of balances out. Nucleophilicity is how readily it will react with that lone pair or that pair of electrons. So it's kinetic. It's kinetically driven. It's driven by the rate constant, not the equilibrium. The equilibrium is driven by the equilibrium constant. The rate's driven by the rate constant. So basicity is thermodynamic and nucleophilicity is kinetic. Okay. So that means that sometimes the strongest base will react first. Sometimes the better nucleophile will react first. Okay, so let's talk about why. They usually do parallel each other really well. For example, negatively charged nucleophiles tend to be strong nucleophiles because that when you protonate them, their conjugate acids tend to be very, very weak. Okay. So when you have two nucleophiles that have the same atom, so we're not comparing, oxygen and nitrogen here, you look at the pKa of the conjugate acid to see which one's the stronger nucleophile. So in this case here, between hydroxide and the acetate ion, which is the stronger nucleophile? If we had the conjugate acid of hydroxide is going to be water, it has a pKa of 15.7, so that's a very weak acid. And the pKa of the conjugate acid of acetate would be 4.8, making it the stronger acid. So the stronger acid is the weaker base. So that makes hydroxide the stronger base and the stronger nucleophile. Okay, and think about it. Alcohols are just above water. So that means the deprotonated alcohol is going to be a better nucleophile than hydroxide, which is deprotonated water, which is going to be a better nucleophile than carboxylic acid, which is going to be better nucleophile than the neutral water and alcohol. Because the neutral water and alcohol have lone pairs, they can act as nucleophiles as well. So for strength here, think about the conjugate acid strength and know that a very strong acid is a very weak base, and a very weak base is a very strong acid. So that means we kind of look down the row here that as we go forward from fluorine to oxygen to nitrogen to carbon, we actually increase nucleophilicity because this is a much stronger base than this. This conjugate acid is so much more weak than this conjugate acid. Okay, so we want to keep that conjugate acid base kind of in our heads. Okay, so stronger the base, the better the nucleophile. Okay, now one of the things that happens with that is we have to worry about steric effects. Now, steric effects are when we have just too many things close around. Imagine you're playing basketball and there's nobody on the court. You can just go and hit the basket with no problem. Then somebody, a tall guy comes over here and gets on this side, so you got to like shoot from this side a little bit. So it takes you longer because you got to avoid the person, and then you got a second person, and they're both standing in front of you, and they're always knocking it down. So then you get a third person, and you can't get anything. So the more things you have in your way, and that is in the way of the carbon that has that polar bond on it, that carbon that's partially positive, the more things that it's going to be harder to get. Now, from the nucleophile side, if I'm a tiny little nucleophile, I can zip in around stuff and get into that position I need to be in to do my substitution. Now, if I get a little bit bigger, I have a long tail on me, maybe a long tail, it's going to take me a little more time to get exactly in the right place. Now, if I'm wearing a parachute and I'm trying to get there, I'm so sterically demanding, I'm not even going to be able to act as a nucleophile anymore. So in that case, we have things like methoxide and ethoxide. They're very strong bases, but they're also very good nucleophiles because they're small. Okay, very good nucleophiles because they're small. But by the time you get to the isopropyl alcohol or this T-butyl here, it's too big. It can't do anything kinetic. It can only do things thermodynamic. And so it's going to be a base. It's not going to act as a nucleophile at all. And so we actually call this one, write this down, T-butoxide is a non-nucleophilic base. So it's just gotten so big, it's just going to wait around for equilibrium to happen, and therefore it's only going to act as a base. But the little zippy, methyl and methoxide and ethoxide can just zip in there and act as their own nucleophiles. Okay. So that's the great part about that. So we said that it was the nature of the atom, where its position is on the periodic table. We're looking at basicity by looking at their conjugate acids and size. All right. So now we want to add one more factor to this, and it's solvent. Okay, we have two classes of solvent we're going to use in this chapter. The first one is what we call protic solvents. Protic solvents are solvents that have a hydrogen bondable hydrogen. So we're looking at water, alcohol, carboxylic acids. That's all I have listed: water, alcohol, and carboxylic acids. So these all have a proton that can hydrogen bond. That means that hydrogen bond can interact within an intermediate, and that interaction with an intermediate will change its nucleophilicity. Okay. The second set of solvents we have are what we call aprotic solvents or non-protic, things that don't have acidic hydrogens, things that don't hydrogen bond. So a classic for that would be our nice little acetone here. It's a ketone. It only has dipole-dipole interactions. There's no hydrogen bonding available. So another one we have here is acetonitrile. And these are all solvents you should know. Write those down. Use flashcards. Acetonitrile. It's polar aprotic. Then we have this one here. This is actually kind of a weird one because it was named for its parent compound, this, which is furan. And you had two double bonds, so they said, I'm going to add two hydrogens on this one and two hydrogens on that one and turn it into tetrahydrofuran. So there's no simpler name, unfortunately. So I guess we could call it cyclooxypentane, but we'll save that for some other day. But we call this THF. THF, it's just a polar aprotic solvent, non-protic solvent. Another one is like acetone, but we replaced one of the carbons with sulfur here. Dimethyl sulfoxide, DMSO. And then we have these two amides here. So the amide, if you'll remember, is this carbonyl nitrogen group here. And this one has a hydrogen here, and we call that dimethyl formamide for formic acid. And then this one looks like acetic acid, so we call that dimethyl acidamide, or DMAC. So these are the ones that we're going to see a lot in here, and we do a lot of different reactions in all these. But you need to know the difference between the protic and the aprotics. Okay, so why do we need to know the difference between aprotics and protics? In a protic solvent, it can hydrogen bond to your ions. And so we can have up to, in this case, water, 8 different water molecules, hydrogen bonding to your ions, satisfying that negative charge. That ion hydrogen bond interaction is much, much stronger than the dipole ion interaction we have with acetone. That's a much weaker bond. That means that negative charge for this bromine is not satisfied with all those dipole charges. It's not being held in. So that means that the bromine with only the dipole charges is more nucleophilic because this one over here has all its charge kind of satisfied, making it less nucleophilic. So when your charge is not satisfied, you are more nucleophilic. Okay. So that means that in the case of This, if you want your bromine or your iodine to be more nucleophilic, you must use a non-protic solvent. Okay, so let's continue on that thought real quick and look at this. So the smaller, more electronegative ions are solvated more strongly and effectively, shielding them from the reaction. Okay. In your protic solvent. So that means nucleophilicity increases down the column of the periodic table. Okay. And as ion size increases. So the bigger the ion, the more nucleophilic it is. As we go down that chain. So ion size is increasing, but notice that that's the reverse of basicity. So the weaker base is the more nucleophilic in the polar protic solvents. And then, so that means it's the opposite of basicity when we have protons, or when we have protons around. That kind of makes sense, right? Because if your basicity should change if you have available hydrogen bonding protons. So what that means is, in the case of a polar protic solvent, look at iodine is more nucleophilic than bromine, which is more nucleophilic than chlorine and fluorine. But if we were to flip that, if we were to take those same ions and put them into polar protic solvents, it changes now. Because the ions are no longer satisfied, we now have fluorine is greater than chlorine, greater than bromine, greater than iodine. It's the backwards of it. So that's very important to know. Polar protic solvents give you iodine as your strongest. Polar aprotics give you fluorine as your strongest. It just inverts the order. Okay. And we know this because of that hydrogen bonding to the ion. Okay. All right. So let's talk about mechanisms. Okay. So let's see. How can we make a new model? Okay. We can make and break a bond at the same time, right? Because we looked at a diagram for that. Okay. So that makes sense. We were making and breaking at the same time. We could also break one first. Notice we broke that pi bond and then and got a charged species out of it. So we could do that too. What about making a bond first? Can we make a bond first? No, that'll violate the octet rule. You can't have 10 electrons. That's why we have to make and break at the same time. So there's only ever 8 electrons there. So we can't do that one. Oh no. Sorry, you guys at home, look away. Don't want to get sick. Okay. Come on. Okay, there we go. Sorry, I touched something on the wrong side of this. So we can't do this right here. So that means we have 2 options for our mechanisms on these substitution reactions. We could make a break a bond same time, which would be a second order reaction, and there'd be 1 hump on our energy diagram. Or we can break a bond first, making an intermediate, meaning we're going to have 2 humps on our energy diagram, and it's going to be a first order reaction. So those are our 2 possible things that we can have. So let's look at this right here. If we go through, so that's what, this is an explanation of why we can't have the third one there. But anyway. So let's start with the first one, making and breaking a bond simultaneously. Okay. So this type of reaction is a substitution reaction, and it has a nucleophile in it, but it took both molecules to be at the same place at the same time. So we call it bimolecular. Okay. So that's where this SN2 comes from. Substitution, nucleophilic, bimolecular. So the great thing about that is we have our nucleophile come in, start making a new bond. Our leaving group starts to leave in our transition state, and we end up getting our substitution product. Okay. So let's look at this again. Notice where this nucleophile is coming in 180 degrees from our leaving group. Why? If we're making and breaking at the same time, it's better to do it opposite each other so that you can't have them both coming in at the same place. So we're going to do it opposite each other. But what does that do to the three other things attached? As we're making the bond here, these things are spreading out to give us room for the nucleophile to come in. And as we're breaking this bond here, that means they're going to be going to the side without stuff on it. We're inverting the stereo center. We have inverted our stereo, our carbon. Okay, we don't have four things on here, so we can't see that it is, but we're having this. So it's like if you have an umbrella and you hit it with wind and it flips inside out, that's what's happening to the things that are attached to the carbon. As you have your nucleophile come in from the inside, it flips the other side out. And so we get inversion of stereo center. Okay. And because we had to have this at the same place as this, we have our second order rate law. The nucleophile concentration and the substrate concentration are both important. So SN2 reaction happens all at one time, is a second order rate law. Okay. So let's look at what the energy diagram would look like that. Well, it happens all at once. We're only going to have one hump. We only have one transition state. Okay, so in this case, we have our transition state. We start off with our reactants. This is our activation energy to get to this transition state. Notice how long these bonds are, because we have to actually can't have more than those 8 electrons, so they have to be really making and breaking at the same time. And then we get that inversion of the stereo center, and we have our products come out here. And our products are lower in energy than our starting material, so it's exothermic or exergonic. So this is a great example of an SN2 reaction with a second order rate law. Okay. So yeah. So I want to draw attention to the fact that when you have an SN2 reaction, you always have inversion of stereo center, okay? Which makes it stereo selective. If you start out with one, you're going to get the inversion of that center. That's the one isomer you're going to get. So that makes it stereo selective, okay? And it happens this way always because of this forming the bond 180 degrees from the bond you're breaking. So you're always going to do this. Now we can draw it a little bit differently too. If we're actually on this lower one here, we have the hydrogen is the small group, and we have two groups here. So we're going to have it come in here and kick this out. Notice we get inversion of stereo center here as well. So it's stereo selective, and you always get inversion. Okay, so let's talk about reactivity. Okay, and the reactivity has everything to do with that transition state. Your nucleophile has to come in 180 degrees away from your leaving group, which means the smaller things you have attached to that carbon, the easier it will be. That means the methyl group is going to be the fastest to react because it only has 3 hydrogens. Okay, so if it only has 3 hydrogens, that means it's going to be easier for that nucleophile to come in from the backside because there's only hydrogens in its way to kick out the leaving group. The next is going to be a primary. It's a little harder. You have 1 R group on there, but you still have 2 hydrogens to get in 180 degrees away from your thing. So that's going to be a little bit slower. Now, once you got 2 R groups here, it gets much slower because now you have 2 carbons with hydrogens on it you're trying to get in between. And then by the time you get to the tertiary, it pretty much doesn't happen at all. Okay, so methyl and primary alkyl halides are great for the SN2 reaction. 2s react a little slower. 3s almost never react at all. So that's going to be really important. Now, if your 1 or 2 has a really big bulky group on there, you know, like a isopropyl or something, it might start to slow the reaction down, but it still should go. Okay, do we see why the substrate changes the rate on these? Okay. So if we look at the energy diagram associated, specifically looking at the activation energy, it's in higher activation energy to get those methyl groups to move to get in this planar configuration. Okay, so our activation energy here is significantly higher because it has to use so much more force to push those methyl groups up. And so it happens at a slower rate. Okay. Now I'm going to save SN2 for the next. Okay, so Wednesday, quiz chapter 5 and chapter 6 up to SN2, definitions, nucleophiles, that kind of stuff. Okay, and then we have spring break. We'll finish most of chapter 6 on Wednesday, and then we'll do chapter 7 after that. We'll have already done a lot of chapter 7 when we finish chapter 6, so it'll be easier to see. All right, any questions there at home? Yes, quiz on Wednesday. Yes, it will be on Canvas. Okay. I'm going to go ahead and stop recording.